Welcome to the Drowsy Astronaut, where we trace the long arc of human ambition. And tonight we begin a journey that spans 1,000 years into the future of spaceflight. This is not a story of rocket launches alone, but of generations who will live and die among the stars, carrying forward the quiet dream that began when our ancestors first looked upward and wondered what lay past the horizon. You can relax, fall asleep, or keep me as a background companion while you work on your own quiet projects. This journey moves slowly through centuries, and each step builds on the last with clarity and purpose. We'll begin, in our own time, the early 21st century, watching humanity take its first permanent steps beyond Earth into the solar system. The moon becomes our closest neighbor once again, not for flags and footprints, but for minds and habitats that grow across decades and expand over centuries. Mars follows, a red world that begins as a destination and slowly transforms into a home for people who will never return to Earth. From there, fusion drives ignite, outer moons awaken, and generation ships depart on journeys measured not in years, but in human lifetimes stacked end to end. By the time we reach the year 3025, humanity will have scattered across multiple star systems, and the species we call human will have changed in ways both subtle and profound, shaped by new worlds. This is a story of adaptation, of patience, of science moving forward one careful experiment at a time, and of the loneliness and wonder that come with leaving home forever. But before we get too far ahead of ourselves, do let me know where you're tuning in from tonight. It is always a gentle pleasure to know that so many corners of Earth gather here together, imagining the future as one big, curious family. So, let's begin. We start in the year 2025, where rockets still burn chemical fuel, and where the International Space Station orbits as the furthest place humans routinely inhabit. The moon has been visited, studied, and abandoned more than 50 years before. But new plans are forming, driven by resources rather than prestige alone. Lunar ice sits hidden in permanently shadowed craters near the poles, and that ice contains water, oxygen, and hydrogen, the building blocks of life and fuel. By 2030, robotic missions confirm the deposits, measure their depth and purity, and engineers begin designing the first permanent outpost near the lunar South Pole. The outpost arrives in pieces, landed by heavy rockets over several years, and crews rotate through 6-month shifts, assembling habitats buried under lunar regolith for radiation protection. The work is slow, methodical, and unforgiving, because the moon offers no atmosphere to slow mistakes, and dust clings to everything, abrading seals and scratching visors. Picture standing inside one of those early habitats, walls humming with recycled air, and through thick viewports you see Earth hanging motionless in the black sky, never rising or setting. The base grows, adding modules for hydroponics, for workshops, for sleeping quarters. And by 2040, a crew of 20 lives there continuously, mining ice and extracting resources. Water becomes fuel through electrolysis, splitting into hydrogen and oxygen. And those gases power small rockets that ferry supplies between the moon and Earth orbit. The economics shift gradually, because launching from the moon requires far less energy than lifting from Earth. And depots in lunar orbit become refueling stations for missions, going deeper into the solar system. Helium-3 appears in the regolith, a rare isotope that might one day fuel fusion reactors. Though that technology remains decades away, still experimental and unproven in 2050. Still, companies and governments invest, building infrastructure on the assumption that fusion will arrive. And the moon becomes a place where people work, not just visit briefly. By 2060, the first children are born on the moon, in rotating habitats designed to simulate Earth gravity. Because doctors worry about development in low gravity, about bones and hearts forming differently. Those children grow up knowing two worlds, Earth through video and the moon through their windows. And some never make the journey downward, choosing to remain where gravity feels lighter and movement easier. Settlements expand across multiple craters, linked by underground tunnels to protect against radiation and temperature extremes. And solar farms stretch across sunlit plains, feeding power into the growing grid. The moon in 2075 is no longer empty. It holds thousands of people. And its economy mines, manufactures, and ships goods to stations orbiting Earth and Mars. Mars, meanwhile, draws the longest gaze, a destination that requires months of travel, and where the conditions challenge every system engineers design. The first robotic missions in the 2020s and 2030s test landing systems, study the atmosphere, and search for underground water locked in ice and ancient aquifers. By 2045, the first crewed mission departs, 6 astronauts sealed inside a ship for 7 months, enduring radiation, muscle loss, and the psychological weight of isolation. They land near the equator, in a region where orbital surveys detected ice just below the surface, and they deploy habitats prefabricated and tested on Earth, now anchored under Martian regolith. The mission lasts 18 months on the surface, conducting experiments, drilling for water, testing life support systems, and every failure teaches lessons that reshape the next attempt. They return to Earth as heroes, but the real work begins with the second mission in 2048, which stays longer and begins building infrastructure meant to last decades. By 2055, a permanent base operates continuously, with crews rotating every 2 years, and supplies arrive regularly from Earth and from lunar manufacturing hubs. Mars dust is everywhere, fine and abrasive, infiltrating seals and coating solar panels, but crews adapt, developing routines for cleaning, for maintenance, for survival. Picture stepping outside a Martian habitat in 2065, suited and pressurized, and looking up at a sky that shifts from butterscotch near the horizon to deep violet overhead. The sun appears smaller, dimmer, providing less warmth than on Earth, and temperatures plunge at night to 100 degrees below freezing. Dust storms can last weeks, darkening the sky and cutting solar power, forcing crews to rely on nuclear reactors buried safely away from living quarters. Yet the landscape holds beauty, vast canyons, ancient riverbeds, and volcanoes larger than any mountain on Earth. And explorers venture farther each year, mapping and studying what lies beyond the base. By 2075, Mars hosts 3 separate bases, each specializing in different research or resource extraction, and the population reaches 200 people, the largest human presence beyond Earth. Underground greenhouses produce food, supplementing shipments from Earth, and engineers experiment with using Martian soil, modified with bacteria and nutrients to grow crops. Children are not yet born on Mars because the low gravity raises too many unknowns, and ethics committees debate whether it is responsible to create lives that may never withstand Earth's pull. Still, some crew members extend their stays year after year, and a few begin to think of Mars as home, even as their bodies adapt slowly to the lighter world. The asteroid belt becomes the next frontier, not for settlement, but for resources, because those tumbling rocks contain metals, water, and rare elements in concentrations Earth can no longer easily provide. By 2080, automated mining drones operate across dozens of asteroids, sending refined materials back toward Earth and Mars on slow, efficient trajectories. Human crews supervise from small stations, rotating through 6-month shifts in microgravity. And the work is lonely, isolated, with only radio contact and the distant sun for company. Yet, the asteroid belt fuels the growing economy of space, providing the raw materials for ships, habitats, and infrastructure. And by 2100, it has become as vital as any mine on Earth. By 2100, the inner solar system holds permanent human presence across multiple worlds, and the Moon and Mars are no longer destinations but neighborhoods, familiar and mapped. Fusion power remains experimental, but progress accelerates, with test reactors achieving net energy gain, and engineers predict commercial fusion within 2 decades. The population in space numbers in the thousands, still small compared to Earth's billions, but growing steadily and no longer dependent on constant resupply from the homeworld. Communication links span the solar system, with delays measured in minutes for the Moon, longer for Mars, and messages carry news, science, and the quiet voices of people building lives far from home. By 2125, the first fusion-powered spacecraft completes its shakedown cruise, cutting travel time to Mars from months to weeks. And suddenly, the outer solar system feels closer, within reach of human ambition. Plans are drawn for missions to Jupiter's moons, to Saturn's rings, to the ice worlds beyond, and a new generation of explorers trains for journeys that will take them farther than anyone has traveled before. Mars begins serious terraforming experiments, releasing greenhouse gases from polar ice, attempting to thicken the atmosphere incrementally, a project that will span centuries. The first century of permanent spaceflight ends not with completion, but with momentum, with infrastructure in place and humanity poised to push deeper into the unknown. The year 2125 marks a turning point, not in spectacle, but in commitment. Because humanity now views Mars not as a place to visit, but as a world to reshape slowly. Terraforming begins in earnest, guided by models refined over decades of observation. And the first step involves releasing carbon dioxide, trapped in the polar ice caps and in subsurface deposits. Nuclear devices are proposed, then debated, then replaced by gentler methods, using orbital mirrors to focus sunlight onto the poles, warming them gradually year by year. The mirrors, each kilometers wide, are assembled in Martian orbit from materials mined in the asteroid belt, and they reflect additional sunlight onto targeted regions, nudging the climate forward. The process is glacially slow, measured in decades rather than years, and scientists caution that visible change will take centuries, not lifetimes. Still, by 2140, atmospheric pressure has risen measurably, enough that suits require slightly less pressurization, and dust storms become more frequent, energized by the warming atmosphere. Surface temperatures climb by a few degrees, averaged globally, and ice begins sublimating at the poles, releasing water vapor and thickening the air. The Martian sky shifts subtly, holding more haze, scattering light differently, and long-term residents notice the change, even as newcomers see only the same red desert. Underground cities expand dramatically during this century because the surface remains hostile despite incremental warming, and radiation protection requires either thick atmosphere or thick rock above. The largest settlement, Mariner City, burrows into the walls of Valles Marineris, using natural canyon shelter and connecting dozens of modules through pressurized tunnels kilometers long. Picture walking through those tunnels in 2150, walls carved from Martian bedrock and lined with metal, and overhead lights mimic Earth's daylight cycle, helping residents maintain circadian rhythms. Side passages lead to greenhouses, workshops, residential quarters, and communal spaces where people gather, and the architecture balances efficiency with the human need for openness and light. By 2160, the population on Mars reaches 10,000, a mix of scientists, engineers, miners, and support staff. And families begin arriving, children included, though birth on Mars remains forbidden by international agreement. Those children grow up in underground cities, experiencing Martian gravity that pulls at roughly 1/3 Earth's strength. And their bones develop differently, lengthening, lightening, adapting to the reduced load. When they visit Earth on rare occasions, the journey itself is manageable, but re-entry into Earth's gravity becomes painful, exhausting, requiring months of physical therapy. Some teenagers refuse the trip entirely, choosing to remain on Mars, and debates flare about whether this creates a permanent separation, a branching of human experience. The first child born on Mars arrives in 2175, despite the international ban, when a pregnancy occurs unexpectedly and termination is refused on personal grounds. The birth is closely monitored, the infant developing in a rotating habitat designed to simulate Earth gravity during critical growth periods. And doctors watch for skeletal, cardiac, or developmental abnormalities. The child grows normally at first, though long-term health remains unknown. And the event forces legal and ethical frameworks to evolve rapidly. By 2180, controlled births are permitted under strict medical oversight, and the first generation of true Martians begins, children who will never call Earth home. Asteroid mining reaches industrial scale by 2150, with dozens of crude stations scattered across the belt, and automated systems hauling metals, water, and volatiles toward processing hubs. The materials fuel construction projects throughout the inner solar system, building ships, habitats, and orbital infrastructure without lifting mass from planetary gravity wells. Water extracted from carbonaceous asteroids becomes the most valuable commodity because it provides drinking water, oxygen, hydrogen fuel, and radiation shielding all at once. A single large asteroid might hold more accessible water than decades of lunar mining, and prospectors stake claims, forming loose corporations governed by treaties written back on Earth. By 2175, a permanent station orbits Ceres, the largest body in the asteroid belt, serving as a hub for mining operations and a waypoint for ships traveling to the outer system. Ceres itself holds subsurface ice, possibly even a liquid ocean beneath its crust. And drilling operations probe carefully, searching for water and testing whether life ever emerged there. The station houses 500 people, rotating crews and long-term residents. And its artificial gravity comes from a slowly spinning torus, enough to prevent bone loss. Life there is quiet, methodical, focused on work, with entertainment limited to virtual experiences and messages from home that carry delays of 20 to 40 minutes. Mars continues its slow transformation, and by 2200, atmospheric pressure reaches 10% of Earth's, still far too thin to breathe, but thick enough to allow liquid water to exist briefly on the surface. Orbital mirrors now number in the dozens, their positions adjusted seasonally, and engineers propose releasing engineered microbes to process soil, producing oxygen and breaking down perch laurets. The microbes are tested exhaustively in sealed domes for decades before release, because contamination of Mars with Earth life raises profound scientific and ethical questions. By 2210, approval is granted for limited release in targeted regions, and the first terraforming organisms spread slowly across Martian soil, metabolizing and multiplying. Greenhouses on Mars grow larger and more ambitious, some spanning hectares under pressurized domes, and crops are rotated carefully, with Martian soil mixed incrementally into Earth-based substrates. The goal is self-sufficiency, reducing dependence on shipments from Earth, and by 2220, Mars produces 70% of its own food, though variety remains limited. Protein still arrives frozen from Earth or grown in vats from engineered yeast, and meals tend toward the practical rather than the pleasurable, though chefs do their best. Still, eating food grown in Martian soil carries symbolic weight, and children raised on Mars feel a connection to the red dust that outsiders cannot fully understand. Communication with Earth now carries a delay of 4 to 24 minutes, depending on orbital positions, and conversations become exchanges of recorded messages rather than real-time dialogue. This delay shapes Martian culture, making the colony more independent in decision-making, and governance structures evolve to handle local issues without waiting for Earth's input. By 2225, Mars elects its first independent council, though still under broader Earth-based treaties, and debates begin about autonomy, taxation, and representation. The seeds of political separation are planted, though full independence remains decades away, and most Martians still consider Earth their ancestral home, even if they never visit. Fusion power becomes commercially viable by 2180, after decades of incremental progress, and reactors on Earth, the Moon, and Mars begin replacing older nuclear and solar systems. The energy density of fusion changes what is possible, allowing ships to accelerate continuously rather than coasting most of the way, and travel times between worlds drop by half or more. The first fusion-powered cargo hauler completes a round trip between Earth and Mars in 4 months, compared to 18 months with chemical rockets, and the economics of space transport shift fundamentally. By 2200, fusion drives are standard for crewed missions, and engineers begin designing ships for journeys to Jupiter, Saturn, and beyond. The outer solar system beckons, its moons rich with water and organic chemistry, and missions are planned to Europa, Enceladus, and Titan, each holding secrets beneath their frozen surfaces. Jupiter's radiation belts remain a formidable challenge, damaging electronics and threatening crew health, but shielding improves using water tanks and magnetic fields to deflect charged particles. By 2220, a crewed mission departs for Jupiter, the journey taking 8 months with fusion propulsion, and humanity prepares to touch the moons of the gas giants for the first time. Mars' transformation continues, the atmosphere thickens year by year, and by 2025 some regions see daytime temperatures rise above freezing, brief windows when water might flow. The journey to Jupiter in 2020 marks humanity's first venture into the deep outer system with living crew, and the ship that makes the crossing, named Galileo's Dream, carries 12 astronauts sealed inside for 8 months, Fusion engines burn steadily, providing gentle acceleration for half the trip, then flipping to decelerate. And the crew experiences a sustained, comfortable push rather than the weightlessness of coasting. Radiation remains the primary hazard, with Jupiter's magnetic field channeling charged particles into deadly belts. So the ship carries thick water shielding and a lead-lined storm shelter for solar events. By 2021, Galileo's Dream enters Jovian orbit, and humanity looks down on the swirling storms of the largest planet, while preparing for the real goal, exploring Europa's hidden ocean. Europa appears from orbit as a cracked white sphere, its surface scored with reddish-brown lines, and those lines are fractures where the ice shell has split and refrozen over geological time. Beneath that ice, perhaps 10 to 20 kilometers down, lies a liquid ocean warmed by tidal flexing, and that ocean may hold more water than all of Earth's seas combined. Scientists have debated for decades whether life might exist there, sustained by hydrothermal vents, and now instruments will probe directly, drilling through the ice to taste the water below. The first landing occurs in 2022, a robotic drill platform set down near a recent fracture zone, and cameras transmit images of ice cliffs towering overhead, blue-white and ancient. The drill descends slowly, melting and boring through ice that resists with alien chemistry. And weeks pass as the mechanism chews downward, sending back temperature and chemical readings. At 14 kilometers depth, the drill reaches a boundary where ice becomes slush, then liquid water, and sensors detect salts, organic molecules, and unexpected thermal signatures. A sample is drawn upward through the borehole, sealed in sterile containers, and analysis begins immediately, searching for cells, amino acids, or any hint of biology. The results are ambiguous at first: organic molecules, yes, but no clear cells. Yet chemical patterns suggest something beyond simple geology, something that might be metabolic. By 2025, 3 more drilling sites operate across Europa, each probing different regions of the subsurface ocean, and evidence accumulates slowly, not of complex life, but of simple chemistry that resembles life's foundations. Microbial mats might exist, clinging to rock near hydrothermal vents far below, or the ocean might be sterile, filled with organic precursors waiting for the right conditions. The question remains unanswered for decades because each sample requires careful study, and contamination from Earth life must be ruled out before any claim can be made. Still, Europa becomes humanity's most intensely studied body beyond Mars, and missions arrive regularly, bringing new instruments and more sophisticated analysis techniques. Picture standing inside the Europan base in 2240, a pressurized habitat anchored to the ice, and through viewports, you see Jupiter hanging huge in the black sky, its bands and storms slowly rotating. The ice beneath your feet is older than civilization, compressed and cold. And somewhere far below, liquid water moves in currents you can only imagine. Radiation from Jupiter pounds the surface constantly, so the base sits partly buried for protection, and shifts outside are limited to a few hours, with crews rotating frequently. The work is patient, methodical, driven by questions that may take generations to answer fully, and those who come here accept the slow pace, the isolation, and the cold beauty of a moon that might harbor life. Enceladus orbits Saturn, a small moon barely 500 kilometers across, but geysers erupt from its south pole, jetting water vapor and ice particles into space. Those geysers feed Saturn's E-ring, and samples collected by passing spacecraft decades earlier showed organic molecules, salts, and hydrogen, suggesting another subsurface ocean, smaller than Europa's but chemically active. By 2250, a mission reaches Enceladus, using Saturn's moons for gravity assists to enter orbit, and landers are deployed near the South Polar vents, where ice cliffs tower and geysers hiss. The plumes make access easier than Europa because material from the ocean is ejected directly into space, and instruments can analyze fresh samples without drilling kilometers through ice. The findings at Enceladus mirror Europa's: organic chemistry and energy sources, but no definitive life, and scientists debate whether the oceans are too young, too cold, or simply unlucky. Still, the potential fuels continued exploration, and by 2270 permanent stations orbit both moons, with crews rotating through 2-year assignments, conducting experiments and maintaining the search. Children do not live here, the radiation and isolation are too severe, but adults volunteer, driven by curiosity and the chance to witness something profound. The outer moons become laboratories, places where humanity tests not just technology, but patience, and where answers emerge slowly, data point by data point. Titan is Saturn's largest moon, bigger than the planet Mercury, and its thick atmosphere, mostly nitrogen with methane haze, hides a surface unlike any other. Lakes and seas of liquid methane and ethane fill basins near the poles, and rain falls occasionally, carving channels and shaping dunes from organic sand. The temperature hovers around -180 degrees Celsius, far too cold for water. But methane behaves there as water does on Earth, cycling through clouds, rain, and evaporation. By 2260, the first human mission lands on Titan, and crew members step onto a shore where liquid methane laps gently at hydrocarbon sand. Picture standing on Titan in 2265, suited against the cold but not needing a pressure suit, because the atmosphere is thick enough to walk in with just thermal insulation and an oxygen supply. The sky above is orange, thick with haze that scatters light into a perpetual twilight, and Saturn is invisible through the clouds, though occasionally moons peer through breaks. Ahead of you stretches a methane sea, its surface rippled by gentle wind, and the shore is made of water ice pebbles, frozen hard as stone in the bitter cold. The landscape feels alien yet strangely familiar, lakes and rivers and weather, but composed of chemistry that on Earth would be considered exotic. Titan offers resources, vast reserves of hydrocarbons that could fuel industry, and water ice makes up the bedrock, accessible with heat and machinery. By 2280, a small research base operates continuously, studying the atmosphere, the lakes, and the prebiotic chemistry, and engineers experiment with using local methane as fuel for power and propulsion. The base becomes a refueling stop for missions exploring the outer system. And Titan develops a reputation as the most comfortable of the outer moons, with its thick atmosphere providing protection from radiation and micrometeorites. Some crew members extend their stays, drawn by the strange beauty and the sense of standing at the edge of known worlds. By 2300, the outer moons host hundreds of people scattered across research stations and mining outposts, and supply lines from the inner system bring equipment, food, and personnel on regular schedules. Fusion drives make the journey feasible, though it still takes months or years depending on the destination, and crews accept long transits as part of the job. Communication delays stretch to over an hour with Earth, making real-time conversation impossible, and messages become letters, exchanged patiently across vast distances. The outer system feels remote, isolated, but humanity adapts as it always has. And those who live there develop their own culture, shaped by cold, distance, and wonder. Mars, meanwhile, continues its transformation. The atmosphere now thick enough that pressurized suits are lighter, and daytime temperatures in equatorial regions sometimes reach above freezing. Engineered microbes have spread across targeted regions, processing soil and releasing oxygen incrementally, though breathable air remains centuries away. The population on Mars exceeds 100,000 by 2300, concentrated in underground cities, and political movements push for full independence from Earth governance. By 2310, Mars declares limited autonomy, managing its own internal affairs while still coordinating with Earth on trade and treaties, and the red planet begins thinking of itself as a world, not a colony. Fusion technology continues improving, reactors becoming smaller and more efficient, and by 2320, even small craft carry fusion drives, making travel throughout the solar system almost routine. The asteroid belt hosts tens of thousands of people mining and refining materials, and the economy of space now rivals some Earth nations in scale. Permanent stations orbit Venus, studying its brutal atmosphere and testing technologies for high-temperature environments, though no one seriously considers settlement there. The inner and outer solar system are connected, linked by trade, communication, and the slow migration of people seeking new opportunities and new horizons. By 2325, humanity has spread throughout the solar system, from Mercury's sunward side to the moons of Saturn, and the species that once knew only Earth now inhabits a dozen worlds. The journey is far from complete because beyond Saturn lie Uranus, Neptune, and the Kuiper Belt. And farther still, the stars beckon with the promise of new systems entirely. Engineers begin designing ships for journeys that will span decades, even generations. And volunteers start training for missions they will not live to see completed. The next phase of human expansion is about to begin, and it will require patience on a scale never before attempted. Fusion propulsion in 2325 has become the standard for all interplanetary travel, allowing ships to accelerate continuously for days or weeks, reaching speeds unimaginable with chemical rockets. Travel time from Earth to Jupiter drops to 3 months, and to Saturn in 5, while the inner system becomes accessible in mere weeks, transforming logistics and commerce. This speed opens the outer reaches of the solar system, where Uranus, Neptune, and countless dwarf planets orbit in the cold, dark, and where humanity has barely sent robotic probes, let alone crewed missions. By 2330, the first crewed expedition departs for Uranus, a journey of 8 months, carrying a crew of 18 scientists and engineers ready to explore the ice giant and its strange tilted system. Uranus orbits the Sun on its side, its rotational axis nearly horizontal, so its poles point toward or away from the Sun during its 84-year orbit. This creates extreme seasons, with each pole experiencing 42 years of daylight followed by 42 years of darkness, and the magnetosphere tilts wildly, tumbling as the planet rotates. The crew arrives in 2331, entering orbit and deploying probes into the pale blue-green atmosphere, studying wind patterns, chemical composition, and the faint rings discovered decades before. Uranus has 27 known moons, and the largest, Titania and Oberon, become targets for landing. Their surfaces covered in ancient ice mixed with rock, cratered and quiet. The mission lasts 3 years, conducting surveys and testing equipment in the extreme cold, where temperatures drop to -200 degrees Celsius and solar energy is a faint whisper. Nuclear and fusion reactors provide power, and the crew relies entirely on stored supplies, because no local resources have been identified as easily accessible. By 2334, the mission returns to the inner system, carrying data that will occupy scientists for decades, but the consensus is clear. Uranus and its moons offer little for settlement, at least not yet. Still, the journey proves that humanity can reach even the distant ice giants, and Neptune becomes the next target on the exploration schedule. Neptune lies farther still, 30 times Earth's distance from the Sun, and its largest moon, Triton, orbits backward, captured from the Kuiper Belt in the distant past. Triton holds nitrogen ice, geysers that erupt dark plumes, and possibly a subsurface ocean, making it one of the most intriguing targets for exploration beyond Saturn. By 2340, a mission reaches Neptune, spending 2 years studying the system, and Triton receives particular attention, with landers deployed to study the geysers and sample the ice. The findings suggest a captured Kuiper object, rich in volatiles and organic chemistry, and Triton becomes a candidate for future resource extraction, though the distance remains daunting. The Kuiper Belt stretches beyond Neptune, a vast region of icy bodies left over from the solar system's formation. And among those bodies are dwarf planets like Pluto, Haumea, Makemake, and Eris. Pluto itself was visited briefly by a robotic probe in 2015, revealing a complex surface with nitrogen ice plains, water ice mountains, and a thin atmosphere. But no humans have yet traveled there. By 2350, fusion drives have improved enough that the journey to Pluto takes 18 months, and the first crewed mission departs, aiming to establish a small research station on the dwarf planet's surface. The crew arrives in 2352, landing near Sputnik Planitia, the vast plain of frozen nitrogen, and they deploy a habitat designed to endure the cold and isolation. Imagine standing on Pluto in 2353, suited against the bitter cold where temperatures drop to -230 degrees, and looking up at a sky filled with stars brighter than anywhere in the inner system. The Sun appears as a bright star, no longer a disk, providing barely any warmth, and Charon, Pluto's large moon, hangs overhead, tidally locked and massive. The landscape around you is eerie, smooth plains of nitrogen ice giving way to jagged water ice mountains, and the horizon curves sharply because Pluto is so small, barely 2/3 the size of Earth's moon. The silence is absolute, no wind, no sound except your breathing and the hum of suit systems, and the sense of isolation is overwhelming, standing at the edge of the known solar system. The Pluto station operates for 5 years, studying the dwarf planet's geology, atmosphere, and interactions with the solar wind, and crews rotate every 2 years, though some choose to extend their stay. Resources are limited, with no easy way to extract water or fuel locally. So the station depends on shipments from the inner system, making it expensive to maintain. By 2360, the station is scaled back to minimal operations, visited occasionally but not permanently staffed, and Pluto becomes a symbol of humanity's reach rather than a hub of activity. Still, the journey proves feasible, and engineers turn their attention to the broader Kuiper Belt, where thousands of objects await exploration. Dwarf planets like Makemake, Haumea, and Eris receive robotic missions over the following decades, and each reveals unique characteristics shaped by different formation histories. Haumea spins so rapidly that it has stretched into an elongated shape, with two small moons orbiting close, and its surface appears to be pure water ice, brighter than expected. Makemake shows signs of a thin methane atmosphere that comes and goes with its orbit, and Eris is slightly larger than Pluto, with a highly reflective surface suggesting fresh ice. By 2370, small automated outposts operate on several Kuiper Belt objects, collecting data and serving as waypoints for deeper missions into the outer solar system. Deep space observatories are constructed in the Kuiper Belt, far from the sun's glare, and these telescopes achieve unprecedented clarity, studying distant galaxies and searching for exoplanets. The lack of interference from sunlight and solar wind makes this region ideal for astronomy, and scientists discover thousands of new planetary systems, cataloging their properties and searching for signs of life. By 2380, the observatories have identified several Earth-like planets within 50 light-years, and debates begin about whether humanity should attempt interstellar travel. The distances are staggering, even the nearest stars are light-years away, and fusion drives, though revolutionary for the solar system, are far too slow for crossing interstellar space in reasonable time. Engineers propose new concepts, ships that accelerate for years using fusion, then coast for decades at a significant fraction of light speed, perhaps 10 to 20%. Such journeys would take centuries, requiring multiple generations to live, work, and die aboard the ship. And the crew that departs would not be the crew that arrives. These ships are called generation ships, and designing them becomes the focus of intense research, because they must function as self-contained worlds, sustaining life and culture across vast timescales. By 2390, construction begins on the first prototype, built in orbit beyond Neptune, using materials from the Kuiper Belt, and engineers test every system for decades before committing to a crewed mission. The prototype is a rotating cylinder 5 kilometers long and 2 kilometers wide, providing artificial gravity through spin, with internal landscapes, farms, and living spaces. Thousands of people could live inside, with closed-loop ecosystems recycling water, air, and waste indefinitely, and nuclear fusion reactors providing power for centuries. The design includes genetic banks, seed vaults, and libraries containing all human knowledge, so the ship carries not just people, but the means to rebuild civilization if needed. Testing reveals countless challenges, from maintaining ecosystem balance to preventing social breakdown over generations, and psychologists study how to structure governance, education, and culture for a population that will never see Earth. By 2400, the prototype has operated continuously for a decade with a crew of 2,000, simulating a generation ship voyage while remaining in the solar system. Problems arise, equipment fails, ecosystems crash and must be rebalanced. But each failure teaches lessons that improve the design. By 2410, a second-generation ship is constructed, incorporating all the improvements, and volunteers begin applying for the first true interstellar mission, knowing they will never return. The target is Proxima Centauri, the nearest star system, 4.2 light-years away, and even at 20% light speed, the journey will take 21 years, plus decades to accelerate and decelerate. Mars by 2400 has become almost unrecognizable from its 2025 appearance, with atmospheric pressure reaching 40% of Earth's, though still too thin and too cold for unprotected humans. Temperatures in equatorial regions sometimes reach 10 degrees Celsius during summer, and liquid water flows briefly in protected valleys before evaporating or refreezing. The population exceeds 5 million, living mostly underground but with surface excursions becoming routine, and Mars now exports manufactured goods, refined metals, and engineered organisms to other worlds. Politically, Mars has gained full independence, maintaining treaties with Earth but governing itself entirely. And Martian culture diverges slowly, shaped by lower gravity, isolation, and a frontier mentality. The asteroid belt has transformed into an industrial hub, with automated factories processing raw materials, and human populations living in rotating habitats scattered among the larger asteroids. By 2420, over 10 million people live in the belt, working in mining, manufacturing, and logistics, and the economy of space now exceeds Earth's in certain sectors, particularly heavy industry. Earth remains the cultural and political center with over 10 billion people, but the balance of power is shifting as off-world populations grow and develop their own interests. Tensions emerge over resource allocation, trade policies, and representation. And the seeds of future conflict are planted, though still managed through diplomacy. By 2425, humanity's presence spans the entire solar system, from Mercury to the Kuiper Belt, and the total off-world population approaches 20 million people scattered across hundreds of settlements. The inner system is heavily industrialized, the outer system remains frontier territory, and the gap between the two regions creates economic and cultural differences. Generation ships are nearly ready for launch, carrying volunteers toward distant stars, and humanity stands at the threshold of becoming a truly interstellar species. The next century will see the first departures, and the slow journey to other stars will begin. The year 2425 marks the completion of Odyssey 1, the first-generation ship designed for interstellar travel, and it orbits beyond Neptune, undergoing final tests while crews train for a journey unlike any before. The ship measures 6 kilometers long, a rotating cylinder that spins to create artificial gravity along its inner surface, and within that space lies an entire world. Forests and farms, rivers and housing, all contained under a metal sky. 20,000 people will live aboard, a population large enough for genetic diversity and cultural continuity, but small enough to manage with finite resources over a voyage spanning multiple generations. The destination is Proxima Centauri, the nearest star to our Sun, and at 20% light speed, the journey will take 21 years of travel after a decade of acceleration. Volunteers have been selected through rigorous screening chosen for health, skills, and psychological resilience, and they understand that they will never see Earth again, nor will their children or grandchildren. Only the great-great-grandchildren, born during deceleration, will see Proxima's light grow brighter than a star, and only they will witness landfall on a world no human has touched. Families board the ship in 2428, bringing children and elders, creating a demographic balance that mimics a small society. And the ship's culture is designed to evolve while retaining core human values and knowledge. Governance is structured as a council, with representatives elected by districts within the ship, and laws are minimal, focused on safety, resource allocation, and conflict resolution. Picture stepping inside Odyssey 1 in 2429, walking through the main corridor that curves upward in both directions, and overhead, or rather on the opposite side of the cylinder, you see buildings, trees, and open sky painted on panels that glow with artificial light. The spin creates gravity, equivalent to Earth's at the outer rim, diminishing toward the central axis. and parks and greenhouses fill the space with life, plants growing under carefully tuned LED spectrums. Housing clusters are designed for privacy and community, small apartments grouped around shared courtyards, and schools teach not just academics, but the ship's systems, because everyone must understand how their world functions. The air smells of earth and growing things deliberately cultivated to remind people of forests, and the sound of children playing mixes with the hum of ventilation and the distant thrum of fusion reactors. The ecosystem aboard is a closed loop with waste recycled through biological and chemical processes, and water circulates through farms, kitchens, bodies, and back again in an endless cycle. Algae tanks and bacterial processes break down organic waste, converting it into fertilizer and clean water, and carbon dioxide from breathing is absorbed by plants and algae, releasing oxygen continuously. Food comes from vertical farms that grow wheat, rice, vegetables, and fruit in dense hydroponic systems. And protein is cultivated from yeast and insect farms, supplemented by fish raised in aquaculture tanks. The balance is delicate, requiring constant monitoring, and biologists work full-time adjusting populations, preventing overgrowth or collapse in any part of the ecosystem. Energy comes from fusion reactors deep in the ship's core, burning deuterium and helium-3 harvested from the outer planets, and the fuel supply is calculated to last 300 years, far beyond the journey's expected duration. Backup systems include solar panels that can collect starlight, though this provides minimal power, and redundancy is built into every critical system, because failure in deep space means death for everyone aboard. The propulsion system is a fusion torch, a directed jet of superheated plasma that pushes the ship forward. And during the acceleration phase, this torch burns continuously for a decade, gradually increasing speed. Once cruising speed is reached, the engines shut down and the ship coasts through the void, with only occasional adjustments to maintain trajectory or avoid interstellar debris. By 2430 Odyssey, one departs, the fusion torch igniting and pushing the ship away from the sun, and crowds across the solar system watch the farewell broadcasts, knowing they will never hear from these travelers again. Communication is possible during the early years, with messages taking months or years to traverse the growing distance. But eventually the ship will be too far, the signal too weak, and silence will fall. Families aboard wave to cameras, recording final goodbyes to relatives staying behind. And children ask when they'll arrive, not yet understanding the scale of time ahead. The ship accelerates smoothly, pushing everyone gently into their seats. And for 10 years this acceleration continues, the sun slowly dimming behind them. Life aboard settles into routines, with work shifts maintaining the ship's systems, teaching children and tending the farms. And entertainment comes from libraries, virtual experiences, and community events like theatre and music. The first generation adapts well because they remember Earth and chose this journey. But psychologists worry about the second generation, children who will grow up knowing only the ship. By 2440, the first children born aboard reach adolescence, and they struggle with identity, because Earth is just a story to them, and Proxima remains decades away. The ship develops its own culture, distinct from Earth's, shaped by confinement and shared purpose, and language begins to evolve subtly, new words emerging for ship-specific concepts. Governance challenges arise as the original crew ages and new leaders emerge, and elections sometimes become contentious, with factions forming over resource allocation or social policies. By 2450, the founding generation begins to die, mourned in ceremonies where their bodies are composted and returned to the farms. Because burial in space is impractical and every atom must be recycled. The second generation takes control, people who remember Earth only from childhood, and their leadership style differs, more pragmatic and less nostalgic. They focus on maintaining systems, preparing the third generation, and managing the slow psychological challenges of confinement. And the ship endures, its mission continuing. Back in the solar system, more generation ships are constructed, each incorporating lessons from Odyssey 1's early years. And by 2460, 3 more ships depart for different nearby stars: Tau Ceti, Epsilon Eridani, and Luyten's star. Each ship carries 20 to 30,000 people, all volunteers, all accepting the finality of their choice. And humanity begins scattering into the galaxy, seeds cast into the cosmic wind. The ships are designed for self-sufficiency, capable of surviving even if contact with home is lost, and each carries the genetic and cultural legacy of Earth, preserving what it means to be human. By 2480, 5 generation ships are traveling through interstellar space, and the solar system has seeded the first wave of humanity's expansion beyond the Sun. Earth and Mars continue evolving, their populations now exceeding 15 billion and 10 million respectively, and the economies of both worlds remain robust, though increasingly interconnected with the broader solar economy. Fusion power has made energy abundant, and environmental restoration on Earth progresses, with carbon levels dropping and ecosystems recovering from centuries of industrial damage. Mars' atmosphere continues thickening, now at 60% of Earth's pressure, and some regions support liquid water on the surface for extended periods, though still too cold for unprotected life. Terraforming remains a multi-century project with no clear endpoint, but progress is visible to each generation that lives there. By 2500, the solar system's population reaches 50 million, spread across hundreds of worlds and habitats. And humanity has become a spacefaring civilization in earnest, no longer confined to a single planet. The generation ships are decades into their journeys, their crews living and dying aboard, and messages from them have ceased. The distance is too great for communication. New technologies emerge, including experimental drives that might one day achieve 30 or 40% light speed. But these remain theoretical, decades away from practical use. The focus shifts to consolidating humanity's presence in the solar system and to preparing additional waves of generation ships for launch in the coming century. By 2520, plans are finalized for a second wave of ships, larger and more advanced, carrying 50,000 people each and aimed at stars within 20 light-years. These ships will take longer to reach their destinations, but they carry more people and better technology, and the hope is that they will establish thriving colonies on arrival. Construction begins on 3 such ships, using materials from the Kuiper Belt and asteroid resources, and volunteers are recruited, though competition is fierce, because the journey represents adventure and purpose. By 2525, the second wave is nearly ready, and humanity prepares to cast more seeds into the galaxy. The second wave of generation ships launches between 2525 and 2530, 3 massive vessels departing for distant stars, and each carries 50,000 people, double the population of the first wave ships. These ships, named New Horizons, Pioneer's Promise, and Distant Star, are technological marvels, incorporating advances in fusion efficiency, ecosystem management, and radiation shielding developed over the previous century. Their destinations are Wolf 359, Lalanda 21185, and Sirius, each between 8 and 9 light-years away, and at 25% light speed. The journeys will take 32 to 36 years of travel after acceleration. The crews are younger this time, with families selected for genetic diversity and skills, and the ships include extensive genetic banks to prevent inbreeding over the centuries-long missions. Life aboard these ships begins with excitement as communities organize and systems are tested in real conditions. But the reality of confinement settles in within the first few years. The spin gravity feels slightly lighter than Earth's, calibrated to reduce structural stress, and people adapt, though some experience nausea or disorientation. Children born during the early years grow up without memory of Earth, and educators struggle to keep the home world relevant through virtual experiences and historical lessons. By 2540, the first generation of shipborne adults takes on leadership roles, and the culture aboard begins shifting subtly, shaped by the unique environment. Picture living aboard New Horizons in 25 and 50, 25 years into the journey, where the sun is no longer visible as a distinct disk, just another bright star in the unchanging sky. You've never set foot on a planet. Your entire life has been lived inside the ship. And Earth is a story your grandparents told, a place of blue skies and endless horizons. The ship is your world, its corridors and parks your landscape. And community matters more than anything because isolation has no cure except each other. Work is varied, maintaining systems, teaching children, tending farms, conducting research, and everyone contributes because survival depends on collective effort. Communication with the solar system ceased years ago as the distance grew too great for practical exchange, and messages now take decades to traverse the void, making conversation impossible. The ships are truly alone, cut off from humanity's birthplace, and this isolation weighs on some, leading to depression or withdrawal. Psychologists work constantly, providing therapy and organizing social events to maintain mental health, and communities develop rituals and traditions unique to each ship, creating identity and purpose. Some ships fare better than others, depending on leadership and culture, and occasional tensions erupt over resource distribution or personal conflicts. Odyssey 1, launched decades earlier, crosses the midpoint of its journey in 2545, and the crew knows that their grandchildren will be the ones to see arrival. The third generation is now in charge, people who never knew Earth and whose parents barely remember it. And Proxima Centauri ahead is still just a star, slowly brightening, but still distant. Systems have held up well, with occasional failures repaired using spare parts and ingenuity, and the ecosystem remains balanced, though requiring constant adjustment. By 25 and 60, the ship prepares for the deceleration phase, which will begin in a decade, and excitement grows as arrival becomes tangible rather than abstract. The deceleration begins in 2570, the fusion torch reversing to slow the ship over another decade, and gravity shifts slightly as acceleration becomes deceleration, a subtle difference the crew feels daily. This phase uses fuel carefully hoarded for the second half of the journey, and engineers monitor every system, because failure now would mean overshooting the target or crashing into it. By 2580, Proxima Centauri dominates the view, a red dwarf star smaller and dimmer than the Sun, and telescopes resolve its planetary system, confirming the presence of at least 2 rocky worlds in orbit. One planet, Proxima b, orbits within the habitable zone, and images show a world slightly larger than Earth, though its atmosphere and surface remain unknown until closer approach. The crew debates which world to approach first, Proxima b or the outer icy planet, and scientists argue for caution, preferring to study from orbit before committing to landfall. By 2585, Odyssey 1 enters orbit around Proxima b, and cameras send back the first close-up images, revealing a world unlike Earth, tidally locked with one face always toward the star. The day side glows in perpetual reddish twilight, while the night side freezes in eternal darkness, and clouds swirl in the Terminator region where heat meets cold. The atmosphere contains oxygen, nitrogen, and traces of methane, suggesting life or at least complex chemistry, and excitement surges through the ship. Robotic probes descend first, testing the atmosphere and landing on the day side near the Terminator, and the data they return shows temperatures around 15 degrees Celsius in some regions, liquid water in pools and streams, and a landscape of reddish rock under a dim sky. No complex life is immediately visible, but microbial mats cover some rocks, and chemical analysis suggests photosynthesis adapted to the red dwarf's light spectrum. By 2590, the first humans descend to the surface, stepping onto alien soil 4 light-years from Earth, and the moment is broadcast back toward the solar system, though the signal will take over 4 years to arrive. The crew plants no flag because they know this world belongs to whatever life evolved here, and they come as observers and students, not conquerors. The colony that follows is careful, small, and respectful, settling in a region where human presence minimizes impact, and science teams study the local ecosystem intensively, documenting every organism found. Life on Proxima b is simple, mostly microbial, but it follows different biochemistry, using different amino acids and nucleotides than Earth life, proving that biology can take multiple paths. Children born on Proxima b grow up under a red sun, their eyes adapting to the dimmer light, and they develop differently, lighter bones in the lower gravity, taller frames. By 2600, the Proxima colony numbers 5,000 people, and they begin calling themselves Proximans, distinct from the humans of Earth. Back in the solar system, the ships launched in the 2530s continue their journeys, and New Horizons reaches Wolf 359 in 2567, finding a system with no habitable worlds but rich in resources. The crew establishes orbital habitats instead, building rotating cylinders around the star, and they mine asteroids and comets, creating a new society entirely in space. Pioneer's Promise reaches Lalande 21185 in 2571, discovering a cold world with subsurface oceans, and they drill through ice to access the water, establishing underwater habitats lit by fusion reactors. Each colony develops uniquely, shaped by local conditions, and humanity begins diversifying, adapting to worlds beyond Earth's template. Distant Star arrives at Sirius in 2575, the brightest star in Earth's night sky, and finds a binary system with no planets in habitable zones but abundant debris disks. The crew decides to build rather than settle, constructing vast space habitats from raw materials, and they create an artificial world, a cylinder tens of kilometers long orbiting the binary stars. By 2600, the Sirius colony thrives entirely in space, and they wonder if planets are even necessary when habitats can be engineered to perfection. 4 human colonies now exist beyond the solar system, and each is developing independently, diverging slowly in culture, language, and biology. By 2620, more generation ships arrive at their destinations, and the number of human-inhabited star systems grows to 8, with populations ranging from a few thousand to tens of thousands on each world. Communication between systems is essentially impossible because even the nearest colonies are light years apart, and messages take years to cross the void. Each colony is alone, self-reliant, carrying forward human legacy but adapting to local conditions. And the concept of a unified humanity begins to blur. By 2625, humanity has become interstellar, scattered across multiple stars, and the journey is only beginning. The colony on Proxima b in 2625 has grown to 15,000 people, spread across 3 settlements near the Terminator Zone, and the world they inhabit feels increasingly like home, even as it remains profoundly alien. The red dwarf sun hangs perpetually at the same position in the sky, neither rising nor setting, and day is a constant dim twilight that bathes everything in rust-coloured light. The night side lies frozen and dark, with temperatures dropping below -100 degrees, and winds howl constantly along the Terminator, driven by the temperature gradient between day and night. Settlers live in the narrow, habitable band where temperatures stay moderate, and their cities are built partly underground for protection from stellar flares that occasionally flare from Proxima Centauri. Stellar flares are a constant danger because red dwarfs are more active than sun-like stars, and radiation spikes can be lethal to unprotected life on the surface. Warning systems detect the flares minutes before they arrive, giving people time to take shelter underground. And agriculture is conducted in greenhouses with radiation shielding, or in hydroponic farms beneath the surface. Children born here grow up understanding the rhythms of flares, learning to read the sky and respond to warnings. And their culture develops around caution, preparation, and respect for the star's temperament. By 2640, Proxima b has its first generation of adults who have never known another world, and they call themselves Proximans without hesitation, considering Earth a distant legend. Picture standing on Proxima b in 2650 outside during a calm period between flares and looking up at the sky that glows deep red near Proxima, fading to purple-black toward the night side. Earth's sun is visible as a bright star in that dark region, and sometimes you wonder if anyone back there remembers this colony or if the solar system has moved on entirely. The ground beneath your boots is rocky, iron-rich soil that stains everything rust-coloured, and pools of liquid water reflect the red sky, surrounded by mats of microbial life that glow faintly in ultraviolet. The air is breathable, though thinner than Earth's, and smells faintly metallic, and you've lived here long enough that returning to Earth gravity would likely cripple you. Biology on Proxima b is studied intensively because it represents the second independent origin of life humanity has encountered, and biochemistry here uses amino acids unknown on Earth, with proteins that fold differently. DNA does not exist here. Instead, life uses a similar but distinct molecule for heredity, and photosynthesis operates using pigments tuned to red and infrared light from the dwarf star. Evolution has produced only simple multicellular organisms so far, nothing more complex than mats and filaments. But the potential is there, and scientists debate whether intelligence might one day emerge here. Ethical guidelines forbid introducing Earth life into the native ecosystem, because contamination could destroy this unique biological experiment, and Proximans take that responsibility seriously. Settlements on Proxima b are designed for self-sufficiency, growing food in underground farms lit by LED arrays, and water is abundant, drawn from underground aquifers and surface pools. Metals and minerals are extracted from local geology, and manufacturing uses 3D printers and automated factories to produce tools, building materials, and replacement parts. Trade with other human colonies is impossible due to distance, so Proximans develop everything locally, creating a culture of ingenuity and self-reliance. By 2660, they've forgotten what it feels like to depend on Earth, and they view themselves as the beginning of a new branch of humanity shaped by this world. Communication with Earth ceased decades ago, the last message received in 2610 taking over 4 years to arrive, and signals from Proxima to Earth would take another 4 years, making conversation across 8-year delays impractical. Occasionally, the colony sends updates, summarizing their progress and discoveries, but they receive no reply, and don't expect one, because Earth may have changed beyond recognition. The isolation is profound, and some Proximans struggle with it, feeling cut off from humanity's main branch, but others embrace it, seeing themselves as pioneers creating something new. By 2670, the colony holds festivals celebrating their independence, marking the anniversaries of landfall and other milestones, and Earth becomes myth, a story told to children but not lived. Children on Proxima b develop differently, not just physically but cognitively, shaped by the unique environment. And educators notice they think about time and space differently than Earth-raised humans. Growing up under a motionless sun changes how they perceive day and night, and language evolves, with new words for stellar flares, terminator winds, and the experience of living on a tidally locked world. By 2680, the Proximan dialect is barely intelligible to a hypothetical visitor from Earth, and culture has diverged, with art, music, and social customs reflecting their unique environment. Some anthropologists worry that humanity is fragmenting, each colony becoming its own species over time, but others argue this is natural, the expected result of spreading across the stars. Technology on Proxima b advances in directions suited to local needs, focusing on radiation shielding and flare prediction. And scientists develop better materials for construction and better crops adapted to red light. Fusion power provides energy, using deuterium harvested from water and helium-3 from gas giant moons in the outer Proxima system. And automated probes mine those resources, returning fuel to the colony. By 2690, Proxima b has its own small space industry, building satellites and habitats in orbit, and the population expands slowly, limited by resources and the carrying capacity of the land. The colony debates whether to establish settlements on Proxima c, the outer icy planet, but resources are stretched and most prefer to consolidate rather than spread too thin. By 2700, the Proxima colony numbers 30,000 people, and children born now are the 5th generation since arrival. And no one alive remembers Earth directly, only through recordings and histories. The colony has become stable, self-governing, and culturally distinct, and they send a final message toward Earth, a summary of their first century and a declaration of independence. That message will arrive in the solar system around 2704, but whether anyone receives it or cares is unknown, and Proximans accept that they may never hear from Earth again. They are alone, building a new civilization on a world lit by a red star, and their story continues, separate from humanity's origin. Other colonies face different challenges, and New Horizons at Wolf 359 struggles with limited resources because the system has no habitable planets, only asteroids and comets to mine. Their population remains small, under 10,000, living in rotating habitats that feel cramped and artificial. And mental health issues are more common, with depression and claustrophobia affecting many. By 2710, some colonists advocate returning to the solar system if possible, building generation ships for the journey back. But others argue they must adapt and thrive where they are. The debate divides the community, and leadership struggles to maintain cohesion, while resources dwindle slowly and the future feels uncertain. Pioneers promise at Lalande 2 Ulaman in 85 fares better, their underwater habitats beneath kilometers of ice proving stable and resource-rich, and the subsurface ocean holds liquid water, warmth from tidal heating, and abundant organic chemistry. The population grows steadily, reaching 20,000 by 2720, and they adapt to living underwater, developing new technologies for submersible cities and aquaculture. Children here learn to swim before they walk, growing up in an environment more alien than Proxima b, and their culture revolves around the ocean, with myths and traditions centered on water and depths. By 2725, Lalande colonists consider themselves aquatic humanity, distinct from planetary settlers, and they wonder if evolution will eventually change them further, adapting to a life spent entirely underwater. Distant Star at Sirius builds the largest orbital habitats, massive rotating cylinders housing 50,000 people by 2720, and their economy thrives on mining the debris disks and manufacturing goods. They have no planet to call home, but they don't miss it, because their habitats are engineered to perfection with controlled climates, beautiful parks, and abundant resources. Sirius colonists view themselves as the future of humanity, freed from planetary constraints, and they argue that planets are ultimately limiting, while space offers infinite room for expansion. By 2725, 4 major human colonies exist beyond the solar system, and each is evolving independently, diverging in culture, technology, and biology. The divergence of human colonies accelerates during the 8th century of expansion, as generations born on alien worlds adapt to environments radically different from Earth. Proxima b's population in 2725 includes children growing noticeably taller and thinner than their ancestors, because the lower gravity, roughly 90% of Earth's, allows bones to lengthen without the same structural stress. Their eyes have adapted to the dim red light, developing slightly larger pupils and enhanced sensitivity to longer wavelengths. And vision under Proxima's glow feels normal to them, while Earth's bright sun would seem painfully intense. By 2750, medical studies confirm that Proximans born on-world have measurably different skeletal proportions and cardiovascular systems, and doctors worry about whether these changes represent the beginning of speciation. Communication delays between colonies and Earth now stretch beyond practical limits, because even at light speed, messages take years or decades to traverse the distances separating human settlements. Proxima b is 4.2 light-years away, meaning any message to Earth takes over 4 years to arrive, and a reply requires another 4, making real-time conversation impossible across the span of a human lifetime. Wolf 359 at 7.9 light-years faces even longer delays, and Sirius at 8.6 light-years must wait nearly 2 decades for a round-trip message. Most colonies stop attempting regular communication with Earth, sending occasional updates but not expecting replies, and the concept of a unified human civilization fades, replaced by independent worlds pursuing their own destinies. By 2750, the solar system has launched a third wave of generation ships. 15 vessels carrying populations towards stars within 30 light-years, and Earth's population has stabilized around 12 billion, with focus shifting to sustainability and cultural preservation. Mars hosts 20 million people, and its atmosphere has reached 70% of Earth's pressure, with oxygen levels rising slowly as engineered organisms spread across the surface, photosynthesizing and releasing gas. Liquid water flows openly in equatorial regions during summer, creating seasonal streams and small lakes. And native Martian life, the simple microbes discovered centuries ago, coexists with introduced Earth species in carefully managed zones. The question of whether Mars should be fully terraformed or preserved, partly wild, divides Martians, and political debates rage about conservation versus expansion. Picture visiting Mars in 2760, landing at Mariner City, and stepping into a pressurized dome that opens to the outside, where the air is thin but breathable with supplemental oxygen, and the temperature hovers around 5 degrees Celsius. You can see the sky, pale salmon pink with wisps of clouds, the first real weather Mars has known in eons. And in the distance, dust devils spin across plains where imported grasses struggle to take root. Children play in the reduced gravity, leaping meters high with ease, and their laughter echoes through the dome, a sound that would have been impossible here just centuries ago. Mars feels alive now, not fully Earth-like, but no longer dead. And the transformation continues, decade by decade, a project that will span millennia before completion. The asteroid belt has evolved into a loose federation of independent habitats, each rotating cylinder or hollowed asteroid governing itself. And the total population exceeds 30 million, making it the largest concentration of humans outside Earth. Mining and manufacturing dominate the economy, with raw materials extracted and refined into ships, habitats, and trade goods. And some asteroids have been completely hollowed out, their interiors carved into vast cities lit by artificial suns. Ceres serves as the unofficial capital, its orbit making it a central waypoint for traffic across the belt. And the station there houses 500,000 people in rotating sections that provide Earth normal gravity. By 2770, belt cultures are fiercely independent, resisting attempts by Earth or Mars to impose regulations, and conflict occasionally flares over mining rights, trade disputes, or political representation. Jupiter's moons have been settled more extensively, with permanent populations on Europa, Ganymede, and Callisto totaling 5 million people by 2780. And the moons serve as bases for exploring the outer system and extracting resources from Jupiter's magnetosphere. Europa's subsurface ocean remains a focus of biological research, with submarines now exploring its depths, and life has been confirmed: simple microbial ecosystems clustered around hydrothermal vents kilometers below the ice. The discovery of a second independent origin of life in the solar system, after Mars microbes, confirms that biology emerges wherever conditions allow. And scientists estimate that life may be common throughout the galaxy, though intelligence remains rare. Ganymede and Callisto provide water ice and metals, fueling industry throughout the Jovian system. And settlements there are entirely underground or under thick ice, protected from Jupiter's lethal radiation. Saturn's moon Titan has become the most comfortable extraterrestrial settlement, with a thick nitrogen atmosphere that allows walking outside with just thermal suits. and the population reaches 3 million by 2790, making it the largest settlement beyond the asteroid belt. The methane lakes and seas provide resources, and the low temperature means materials behave differently, with water ice as hard as rock, and engineers have learned to build structures using local materials frozen solid in the minus 180-degree cold. Children on Titan grow up skating on methane ice, sailing boats on ethane seas, and breathing oxygen from tanks, but otherwise experiencing a world that feels almost Earth-like in its weather and landscapes. The orange haze in the sky filters sunlight into perpetual twilight, and Saturn, though invisible through the clouds, occasionally appears during breaks, a stunning sight that never loses its wonder. By 2800, humanity's solar system population exceeds 100 million, scattered across dozens of worlds and hundreds of habitats. And the species has become truly multiplanetary, no longer dependent on Earth for survival. Earth itself remains the cultural heart, with the largest population and deepest history, but power is distributed now, with Mars, the asteroid belt, and the Jovian system each wielding significant economic and political influence. Tensions rise over resource allocation, with outer system colonies arguing they receive too little support while contributing immensely to the economy, and Earth counters that it provides the technological and cultural foundation for all human civilization. By 2810, a solar parliament is established, with representatives from each major settlement region, and debates over autonomy, trade, and mutual defense dominate the political landscape. Meanwhile, the distant colonies at other stars continue evolving independently, and Proxima B's population reaches 60,000 by 2800, spread across 5 settlements in the Terminator Zone. Proximans have developed unique technologies suited to their world, including advanced flare prediction systems and radiation-resistant crops, and their culture revolves around community resilience and preparation for stellar storms. Language on Proxima B has diverged significantly from solar system languages, with new vocabulary for their environment and grammatical structures that reflect their cyclical view of time under an unmoving sun. By 2820, genetic studies confirm that Proximans are measurably different from Earth humans, with adaptations to lower gravity and red light becoming heritable, and scientists debate whether to call them a subspecies or simply an adapted population. Wolf 359 colony has struggled, and by 2790, the population has declined to 7,000 as people choose not to have children in the artificial habitats, and morale remains low despite efforts to improve living conditions. The colony debates abandonment, potentially building a generation ship to attempt the journey to another system, but resources for such a project are limited and most simply endure, hoping for technological breakthroughs. Some colonists enter long-term cryogenic suspension, hoping to wake when conditions improve or when rescue arrives from the solar system, though no rescue mission is planned or likely. By 2820, Wolf 359 is considered a cautionary tale, proof that not all human colonies will succeed, and that space expansion requires habitable worlds or abundant resources. Lalande 21185 underwater colony thrives, expanding their subsurface cities beneath the ice, and the population reaches 40,000 by 2800 comfortable in their aquatic environment. Children born here spend most of their lives underwater, developing enhanced lung capacity and comfort with pressure changes, and some scientists suggest that over millennia, Lalande colonists might evolve toward amphibious adaptations. Their culture centers on exploration of the vast ocean, which remains largely unmapped despite centuries of habitation. and expeditions venture deeper, discovering thermal vents, unique mineral formations, and diverse microbial ecosystems. By 2820, Lalande colonists propose a philosophy called deep adaptation, arguing that humanity's future lies in oceans rather than surfaces. And they begin outreach to other colonies, sharing their technological and cultural insights. Sirius orbital habitats have grown into a massive complex, interconnected cylinders housing 120,000 people by 2810, and the economy is the most advanced of any colony, with sophisticated manufacturing and a thriving arts culture. Because they have no planet to constrain them, Sirius colonists build freely, creating habitats of enormous size and complexity, and architects design structures impossible under planetary gravity, soaring towers and suspended gardens. Art flourishes here, with zero-gravity sculpture and light installations that use the binary star's illumination. And Sirius becomes known across human space as the cultural capital, sending out recordings and designs that inspire others. By 2820, Sirius colonists are wealthy, trading manufactured goods for raw materials from nearby systems, and they consider themselves the apex of human achievement, the proof that artificial habitats surpass planets. Back in the solar system, scientists detect a troubling long-term trend. Because the sun is gradually brightening as it ages, a natural process that will continue for billions of years. By 2800, models predict that within 500 million years, Earth will become uninhabitable without intervention, and discussions begin about whether to engineer shade structures or eventually move Earth's orbit outward. Mars will benefit from the increased heat, its transformation accelerating, but Earth faces a distant deadline, and some argue humanity should begin planning now for the eventual evacuation or protection of the home world. By 2825, the Solar Parliament commissions studies on megastructure engineering, considering projects like solar shades or orbital rings, and the scale of thinking shifts toward projects spanning thousands of years. The second wave of generation ships launched in the late 2500s begins arriving at their destinations in the 2820s and 2830s. And these newer ships carry larger populations and better technology than the pioneering first wave. A ship named Unity reaches Tau Ceti in 2828, finding a system with 5 planets, and one world, Tau Ceti E, orbits in the habitable zone with an oxygen-rich atmosphere and liquid water oceans. The crew enters orbit cautiously, scanning the surface for signs of life, and they discover vegetation, green and purple photosynthetic organisms covering vast continents, but no animals, no intelligence, only plants and microbes. This is the first time humanity encounters a world with complex life already established, and protocols for non-interference, debated for centuries, are now tested in practice. The colonists decide to settle on uninhabited islands, minimizing impact on the native ecosystems. And by 2835, Tau Ceti E hosts a small settlement of 10,000, growing food in greenhouses and studying the alien biosphere. The native plants use chlorophyll analogues that absorb different light wavelengths, giving them purple and blue-green hues. And biochemistry here is similar to Earth's, but distinct enough to prevent cross-contamination. Children, born on Tau Ceti E, grow up surrounded by alien life, learning to identify native species and understanding the responsibility of living as guests on another world. And their culture emphasizes conservation and respect for the biosphere. By 2850, Tau Ceti has become humanity's first biologically rich colony, a place where humans live alongside an independent tree of life. And scientists there publish studies that reshape understanding of how biology evolves. Another second-wave ship, Endeavour, reaches 61 Cygni in 2832, finding a binary star system with multiple rocky planets. But none have breathable atmospheres, requiring domed settlements and extensive life support. The colony establishes itself on the largest planet, a Mars-like world with subsurface water ice, and by 2840 the population reaches 15,000, focused on mining and terraforming feasibility studies. Resources are abundant, and the colony exports refined materials to nearby systems using slow, automated cargo vessels, establishing trade networks that span light years, though shipments take decades to arrive. By 2860, 61 Cygni has become a manufacturing hub, building ships and habitats for other colonies, and the economy grows steadily despite the isolation and harsh conditions. By 2850, humanity inhabits 14 star systems beyond the solar system, with a total off-world population approaching 300,000 spread across colonies light years apart. Each colony develops independently, and cultural differences become stark, with languages, customs, and even basic values diverging, making the concept of unified humanity increasingly abstract. Some colonies maintain democratic governance, while others adopt council systems, technocracies, or even hereditary leadership structures. And political philosophies evolve to suit local conditions and populations. Religion also diversifies, with new faiths emerging on distant worlds, often blending Earth traditions with responses to alien environments. And spirituality on a tidally locked world differs profoundly from that under a binary star. Communication between colonies is attempted through laser transmissions, focused beams carrying messages across light years. But the time delays make coordination impossible, and each system must be self-reliant. By 2860, a proposal emerges to create a quantum communication network, using entangled particles to theoretically enable instant messaging. But physics remains unclear on whether information can actually be transmitted this way, and experiments are ongoing. If successful, quantum communication might reunify human civilization across the stars, but if it fails, humanity will remain fragmented, each colony an island evolving independently. By 2880, the experiments show promise but remain inconclusive, and the dream of instant interstellar communication stays just out of reach. Back in the solar system, Earth's population has stabilized at 11 billion, with strict environmental protections maintaining ecological balance. And technology has advanced to the point where resource scarcity is rare, fusion power providing abundant energy. Mars hosts 30 million people by 2870, and the atmosphere is now thick enough that humans can walk outside with only oxygen masks, no pressure suits required, and temperatures in equatorial regions reach 20 degrees Celsius during summer. The transformation of Mars is nearly complete, with only the final steps of increasing oxygen to breathable levels remaining, and engineers estimate another 2 centuries before the atmosphere supports unassisted human respiration. Martian culture has fully matured, with its own literature, art, music, and political identity, and many Martians have never visited Earth, considering the red planet their true and only home. The asteroid belt's population reaches 50 million by 2880, and governance becomes increasingly contentious as habitats argue over mining rights and political representation, leading to the Belt Confederation, a loose alliance that manages disputes and coordinates defense. Pirates occasionally raid cargo shipments between habitats, and the Confederation maintains a small fleet of patrol vessels, though violence is rare and most conflicts are resolved through arbitration. Belt culture emphasizes independence and self-sufficiency, with each habitat developing unique customs, and some habitats specialize in manufacturing, others in agriculture, creating an interdependent economy despite political fragmentation. By 2900, the Belt is effectively an independent nation, no longer deferring to Earth or Mars for governance, and the Solar Parliament recognizes their autonomy in a revised treaty. Jupiter's moons have become centers of scientific research, with permanent populations totaling 8 million by 2890, and Europa's subsurface ocean has been extensively explored, revealing ecosystems clustered around hundreds of hydrothermal vents. Life there remains simple. No complex organisms or intelligence, but the diversity of microbial species is staggering, and biologists estimate thousands of unique lineages, each adapted to specific chemical conditions. Ganymede serves as the administrative hub for the Jovian system, with a large rotating habitat providing Earth normal gravity for long-term residents. And Callisto has become an industrial center, refining water ice and metals for export throughout the system. By 2900, the Jovian system is the third most populous region after Earth and the asteroid belt, and politically, it aligns more with the belt than with Earth, valuing independence and local governance. Saturn's moon Titan hosts 5 million people by 2895, and the colony has developed a unique culture around its methane lakes and seas, with sailing and underwater exploration as central cultural activities. The thick atmosphere allows for aviation using simple winged craft, and Titan has a thriving aerospace industry building atmospheric planes, and children learn to fly almost as early as they learn to walk. Music on Titan is distinctive, using instruments that resonate in the thick nitrogen atmosphere, and festivals celebrate the seasonal changes in methane weather, with storms and calm periods marking the cultural calendar. By 2900, Titan considers itself the most successful outer system colony, balancing comfort, resources, and quality of life. And immigration from other colonies is common, though the journey from the inner system takes months, even with fusion drives. The sun's gradual brightening becomes a more pressing concern by 2900 as models refine predictions of Earth's future habitability. And temperatures on Earth have risen measurably over the past centuries, though still within manageable ranges. Scientists propose several megastructure solutions, building a massive orbital shade to reduce incoming sunlight, constructing a ring of solar collectors to harvest energy while dimming the sun's effect, or engineering Earth's orbit to gradually move it outward as the sun brightens. The third option is the most radical, requiring enormous energy expenditure over thousands of years. But proponents argue it preserves Earth in its natural state, rather than relying on artificial structures that might fail. By 2910, the Solar Parliament approves funding for preliminary studies of orbital engineering, and test projects begin using small asteroids, moving their orbits with sustained ion drives to prove the concept. By 2920, humanity's presence in the solar system peaks at 200 million people, with comfortable living conditions on multiple worlds, and the species has achieved a level of stability, and prosperity unimaginable to the pioneers of the early space age. Interstellar colonies continue growing, now numbering 20 systems with a combined population of 500,000, and new generation ships depart regularly, carrying volunteers towards stars within 50 light-years. The divergence between solar system humans and interstellar colonists widens, with genetic and cultural differences becoming more pronounced. But most accept this as the natural consequence of spreading across the galaxy. By 2925, humanity is no longer one species in any practical sense, but a family of related populations adapting to wildly different environments. And the journey continues, pushing ever outward into the cosmic dark. The year 2925 marks a millennium since the first permanent lunar base, and humanity pauses to reflect on the journey from a single planet to dozens of star systems. Though celebration is fragmented, each colony marking the milestone according to its own calendar and customs. Earth hosts the largest ceremony, with representatives from Mars, the Belt, and the Jovian moons gathering in virtual forums. But the interstellar colonies are too distant, and their messages arrive years late, recordings of celebrations already concluded. Proxima B's message, sent in 2921, arrives in 2925, showing Proximans who look noticeably different from Earth humans. Taller, with larger eyes and skin tones adapted to red light, and speaking a language that requires translation despite English roots. The recording reminds Earth dwellers that humanity is diverging, becoming multiple species. And some find this troubling, while others see it as the natural and beautiful result of adaptation. By 2950, humanity inhabits 35 star systems, with populations ranging from a few thousand to over 100,000 on the most established colonies, and the total interstellar population exceeds 1 million people scattered across light years. Each colony faces unique challenges, some thriving on habitable worlds, while others struggle in harsh environments requiring domed cities or orbital habitats. And natural selection operates at the colony level, with some settlements failing while others flourish. Epsilon Eridani colony, established in 2880, has grown rapidly to 90,000 people by 2950. Because the system contains multiple rocky planets with accessible resources and moderate conditions. They've established settlements on 3 different worlds, creating a multi-planetary civilization within their own system. And by 2960, Epsilon Eridani humans consider themselves a regional power, capable of launching their own generation ships to nearby stars. Picture living on Epsilon Eridani C in 2960, a world slightly larger than Earth, with higher gravity that makes every movement feel heavier. And children born here develop stronger bones and muscles, adapted to the increased pull. The sky appears orange during the day because Epsilon Eridani is a younger, more active star than the Sun, and stellar flares are common, requiring robust radiation shielding for all settlements. Your ancestors came from Earth, but that world is now 10 light years away, and no ship has ever made the return journey, nor would you want to attempt it, because this is home now. The colony sends messages to nearby systems, Tau Ceti and others, proposing trade and cooperation, though responses take decades, making negotiation a slow, patient process spanning generations. Trade between interstellar colonies is theoretical rather than practical in most cases, because even at fusion drive speeds, cargo takes decades to travel between stars, and the economics rarely justify shipping physical goods across such distances. Instead, colonies trade information, sending scientific discoveries, technological blueprints and cultural works via laser transmission. And this exchange enriches all participants despite the time delays. By 2970, a loose network of cooperating colonies has formed, sharing knowledge and maintaining cultural ties despite the impossibility of physical travel. And this network is called the Human Diaspora Cooperative, though membership is voluntary and enforcement non-existent. The cooperative establishes standards for distress signals and protocols for assisting failing colonies, though actual rescue across light years remains impossible with current technology. Some colonies choose extreme adaptation strategies, modifying themselves to suit their environments rather than terraforming worlds to suit humans. And genetic engineering, once controversial, becomes routine as colonies pursue survival. Gliese 67 CC colony, established on a super-Earth with gravity 50% higher than Earth's, begins a program of genetic modification in 2965, engineering children with denser bones, stronger hearts, and enhanced muscle tissue to thrive in the crushing pull. Within 2 generations, Gliese colonists are visibly different from baseline humans, shorter and stockier with barrel chests. And they embrace these changes, seeing them as necessary and even desirable adaptations. Other colonies pursue different modifications: enhanced vision for dim red dwarf light, lung adaptations for thin atmospheres, or increased radiation resistance. And by 2990, human has become a broad category encompassing dozens of distinct populations. Aquatic adaptation proceeds furthest at Lalande 2185, where the underwater colony has thrived for centuries. And by 2980, genetic engineers propose modifications for permanent aquatic life, enhanced lung capacity, webbed digits, streamlined bodies, and the ability to hold breath for extended periods. Volunteers undergo the modifications, and their children grow up more comfortable underwater than on land. And by 3000, Lalande colonists rarely visit the surface, living entirely in subsurface cities lit by bioluminescent organisms. They call themselves Aquans, distinguishing themselves from terrestrial humanity. And their culture revolves around the ocean, with mythology and art centered on depth, pressure, and the mysteries of their world's vast, unexplored seas. By 3010, Aquans propose further modifications, including gills grown from modified lung tissue, and debate rages about whether this crosses a line from adaptation into creating a new species entirely. Digital consciousness emerges as another adaptation strategy, particularly among colonies with limited physical resources, and some individuals choose to upload their minds into computer substrates, living as software rather than biological organisms. Sirius Colony pioneers this technology, and by 2990, 20% of their population exists as digital entities, living in virtual environments, while their physical bodies are either discarded or maintained in cryogenic storage. Digital humans experience time differently, able to slow or accelerate their perception, and they can explore virtual worlds of unlimited complexity, though they sacrifice physical sensation and embodiment. By 3000, Sirius Colony is split between physical and digital factions, each pursuing different visions of humanity's future, and tensions arise over resource allocation, with digital minds requiring far less physical infrastructure. Back in the solar system, Earth's population has declined slowly to 9 billion by 3000, as many choose to emigrate to Mars or the Belt. And the home world focuses on environmental restoration and cultural preservation. Mars is finally breathable. its atmosphere reaching oxygen levels sufficient for unassisted human respiration by 2995, and the celebration is solar system-wide, marking the completion of a 900-year terraforming project. Walking on Mars without a suit becomes possible, though the air is thin, like high-altitude Earth, and temperatures remain cold, averaging around 10 degrees Celsius globally, with warmer regions near the equator. Martian population reaches 50 million by 3000, and Mars now rivals Earth culturally and economically, with some arguing it has surpassed the home world in vitality and innovation. The asteroid belt's population stabilizes around 70 million, with hundreds of independent habitats forming a loose but functional confederation, and belt culture is fiercely libertarian, valuing individual freedom and minimal centralized governance. Some belt habitats have grown enormous, hollowed-out asteroids housing millions in rotating sections, with interiors designed as vast parklands, cities, and industrial zones, each habitat a self-contained world. By 3010, the belt is the manufacturing center of the solar system, producing ships, habitats, and technology exported throughout human space. And belt engineers are renowned for their ingenuity and willingness to attempt audacious projects. Politically, the belt maintains independence from Earth and Mars, though trade ties remain strong, and the three regions form a balanced triumvirate governing the solar system through negotiated cooperation. Jupiter's and Saturn's moons host 20 million people combined by 3020, living in underground cities or orbital habitats, and the outer system remains frontier territory, less densely settled but rich in resources. Europa's subsurface ocean continues yielding biological discoveries, with new microbial species identified regularly. And some scientists propose introducing Earth-derived organisms as an experiment in panspermia, though this remains controversial. Titan has become an aerospace hub, manufacturing lightweight craft suited for its thick atmosphere, and Titan culture revolves around flight, exploration, and the beauty of methane seas under orange skies. By 3020, the solar system is mature, its populations stable and its economy diversified, though the sun's gradual brightening remains a long-term concern, requiring ongoing mitigation efforts. Interstellar colonies now number 50 systems by 3020, with a combined population nearing 2 million, and new generation ships depart regularly, carrying volunteers towards stars within 100 light-years. The farthest colony, at Ross 128, is 10 light-years from Earth, and messages from there take a decade to arrive, delayed reports of a world slowly being transformed into habitat. Each colony is effectively independent, self-governing, and self-sufficient, and the diaspora cooperative provides cultural connection but no political unity, because governance across light years is impossible with relativistic delays. By 3025, humanity has become a scattered species, adapted to dozens of environments and evolving independently on worlds across 100 light-years of space. The 11th century of human spaceflight sees the species embracing radical diversity, with populations adapting to environments that would have seemed impossibly alien to the first space pioneers. And some colonies pursue transformations so extreme that they challenge the very definition of human. Kepler 442 B colony, established on a tidally locked super-Earth orbiting a red dwarf, begins a program of extreme adaptation in 3030. Modifying colonists to tolerate high gravity, low light, and near-constant radiation from stellar flares. Their children are engineered with dense skeletons, redundant organ systems, and melanin-rich skin that darkens almost to black for UV protection. and by 3050, Kepler colonists are visibly distinct, shorter and more robust than baseline humans, their eyes enlarged and sensitive to infrared. These adaptations spark debate across human space about the limits of modification, and some colonies argue that Kepler colonists have crossed the line into creating a new species, while others insist all variations remain human at the core. Other colonies pursue even more radical paths, and LHS 1140 settlement on an ocean world with no land surface modifies colonists for permanent aquatic existence, giving children gill slits developed from modified lung tissue, webbed hands and feet, and streamlined bodies. By 3060, these aquans rarely surface, living in underwater cities lit by bioluminescent algae and breathing dissolved oxygen directly from water. And their culture becomes so distinct that communication with terrestrial humans requires extensive translation, not just of language but of concepts. They experience the world through sonar and pressure sensitivity, senses that land-based humans lack, and their art and music reflect these perceptions, creating works that other humans find alien and beautiful. By 3080, aquans propose further modifications, including altered metabolism for deep-sea pressure tolerance, and some suggest they are becoming a new species, Homo aquaticus, separate from Homo sapiens. Digital consciousness colonies expand dramatically, particularly at Sirius, where 70% of the population has uploaded by 3040, living in vast virtual environments that span simulated worlds of staggering complexity and beauty. These digital humans experience subjective time at variable rates, able to live centuries in subjective experience while only years pass externally. And their society evolves rapidly, developing philosophies and cultures incomprehensible to biological minds. Some digital colonists maintain bodies in storage, occasionally returning to physical form for specific experiences, but most abandon embodiment entirely, considering it a limitation rather than an essential aspect of humanity. By 3070, Sirius digital society has diverged so completely that communication with biological humans becomes difficult, requiring specialized translators who can bridge the conceptual gap between embodied and digital existence. Asteroid habitats in remote systems pursue their own unique path, building massive rotating cylinders and hollow worldlets entirely divorced from planetary gravity. And by 3050, millions of people live entirely in artificial environments, never touching a natural world. These space-adapted humans develop their own physical changes over generations: reduced bone density, elongated bodies adapted to low or zero gravity. And eventually, some lines become unable to tolerate planetary gravity without extensive medical intervention. By 3090, space-adapted humans are recognized as a distinct population, sometimes called Homo spatialis, and they argue that planets are evolutionary dead ends, that humanity's future lies in the infinite expanse of constructed habitats. Their culture emphasizes engineering and artificial beauty, creating habitats of breathtaking design, rotating gardens in space lit by captured starlight, and architecture becomes their highest art form, limited only by physics and imagination. Ancient Earth by 3050 has become something of a museum world, with population declining to 7 billion as people emigrate to more dynamic colonies, and the planet focuses on preservation, maintaining historical sites and natural ecosystems as heritage for all humanity. Pilgrimage to Earth becomes common among interstellar colonists, with generation ships occasionally making the decades-long journey to visit humanity's birthplace. And tourists, from modified populations walk Earth's surface wearing exoskeletons or environmental suits, marveling at the world their ancestors knew. The experience is often transformative, connecting far-flung humans to their common origin. And Earth maintains this role deliberately, refusing to modify itself further, preserving the blue world as it was. By 3070, Earth's main export is culture, art, literature, music, and philosophy that serves as common ground for the scattered human family. And the home world becomes a symbol of unity, even as humanity diverges physically. Mars continues thriving, its population reaching 70 million by 3080, and the planet is fully terraformed with breathable atmosphere and comfortable temperatures. And Martians have developed a distinct culture centered on independence, innovation, and respect for the long transformation their ancestors achieved. The Red Planet exports technology and expertise in planetary engineering, and several colonies hire Martian consultants to guide their own terraforming projects, spreading the lessons learned over 9 centuries. Martian literature and philosophy emphasize patience, long-term thinking, and collective effort. And these values influence cultures throughout human space, even on worlds that never needed terraforming. By 3100, Mars is culturally and economically equal to Earth, and some argue it has surpassed the home world in vitality. And the two planets maintain friendly rivalry, each proud of their achievements. Quantum communication research finally succeeds in 3085, with scientists at Ceres achieving instantaneous communication using entangled particles across a light year, and the breakthrough promises to reunify human civilization by eliminating communication delays between colonies. The technology requires enormous infrastructure, with entanglement generation stations and quantum repeaters needed at both ends of each link. But by 3095, several major colonies are connected, able to exchange messages instantly across dozens of light years. Proxima b connects to the solar system network in 3098, and for the first time in centuries, real-time conversation occurs between Earth and the distant colony. And both populations weep at the reunion, realizing how isolated they had become. The network expands steadily, and by 3110, 20 star systems are linked, creating a quantum web that allows humanity to function as a unified civilization despite vast physical distances. Cultural exchange accelerates with instant communication, and colonies share art, music, scientific discoveries, and philosophical insights in real time. And humanity experiences a renaissance as ideas cross-pollinate between diverse populations living in radically different environments. Some colonies share their genetic modifications, allowing others to adopt successful adaptations. And medical technology advances rapidly as diverse populations contribute insights from their unique experiences. Political cooperation also becomes possible, with the diaspora cooperative evolving into a true interstellar government coordinating policy across human space. Though enforcement remains impossible, and participation is voluntary, based on mutual benefit rather than coercion. By 3120, humanity feels unified again, despite physical diversity and distance, and the quantum network is considered one of the great achievements of human civilization, second only to spaceflight itself. Religious and philosophical movements spread across the network, some old and some new, and faiths adapted to alien worlds find followers on distant colonies, creating truly universal spiritual communities. A new philosophy called panhumanity emerges in 3105, arguing that all modified populations remain fundamentally human regardless of physical form, and that consciousness and culture, not biology, define humanity at its core. This view gains wide acceptance, easing tensions between modified and baseline populations, and by 3115, most colonies embrace pan-humanity, celebrating diversity while maintaining connection to shared heritage. Some purists resist, arguing that extreme modification threatens humanity's essence, but they remain a minority, and the broader trend favors acceptance and exploration of what humans can become. By 3120, humanity inhabits 70 star systems with a combined interstellar population exceeding 5 million. And the solar system hosts 300 million people across Earth, Mars, the Belt, and the outer moons. New generation ships depart regularly towards stars within 200 light-years, and some carry populations already modified for their destinations, pre-adapted to the worlds they will settle. Technology continues advancing, with fusion drives reaching 40% light speed and new propulsion concepts under development. And some scientists propose antimatter rockets that might eventually achieve 70% light speed, though practical implementation remains decades away. The pace of expansion accelerates, and projections suggest humanity will inhabit 200 star systems by the year 3200, spreading across a sphere of space hundreds of light-years in diameter. Ancient archives from Earth are distributed across the quantum network, ensuring that human history and knowledge survive even if individual colonies fail. And every settlement maintains backup copies of literature, science, art, and historical records spanning from prehistory to the present. This cultural preservation effort, called the Memory Project, ensures that no matter how far humanity spreads or how much we change, the story of our origins remains accessible to all descendants. Children on distant worlds learn about Earth's oceans and forests, about Mars' transformation, about the first-generation ships and the pioneers who ventured into the unknown. And these stories connect them to the broader human family despite never meeting anyone from other colonies. By 3125, the Memory Project has become a pillar of human civilization, and historians argue it may be the most important legacy we leave to future generations. Some colonies fail despite best efforts, and by 3120, 5 settlements have been abandoned or lost contact entirely. And the causes vary. Resource depletion, ecosystem collapse, social breakdown, or catastrophic accidents. Wolf 359 colony, struggling for centuries, is finally evacuated in 3105 with assistance from nearby systems, and the survivors resettle at Epsilon Eridani, carrying the painful lessons of failure with them. These failures remind humanity that space is unforgiving and that survival requires constant vigilance, but they also demonstrate the resilience of the species, our ability to adapt, assist each other, and persist despite setbacks. By 3125, protocols for colony rescue and resource sharing are well established through the quantum network, and humanity approaches space expansion with mature understanding of both its possibilities and its dangers. Picture the state of humanity in 3125, 1,000 years after the first permanent lunar base, and see a species transformed, scattered across 70 star systems, adapted to dozens of environments, some barely recognizable as the humans who first looked up at the moon. We swim in alien oceans, fly through methane skies, live in digital simulations, and walk on worlds lit by red dwarf stars. And yet, we remain connected through culture, history, and the quantum web that carries our voices across the light years. The journey from Earth to the stars took a millennium of patience, innovation, and sacrifice, and it continues still, with new ships departing and new worlds awaiting discovery beyond the current frontier. Humanity has become a galactic species in infancy, taking our first steps into a cosmos that stretches billions of light years, and the future ahead contains possibilities we can barely imagine. We have traveled together through 1,000 years of human spaceflight, from the first permanent lunar base in 2030 to a civilization scattered across 70 star systems in 3125. And the journey has transformed us in ways both profound and subtle, changing what it means to be human. Looking back from this distant future, we can see the long arc of expansion, how chemical rockets gave way to fusion drives, how single-planet humanity became interstellar, how one species diversified into many populations adapted to alien worlds. The first steps were small, cautious, driven by curiosity and necessity, and each generation built upon the work of their ancestors, solving problems and pushing boundaries until the impossible became routine. Tonight, as we reach the end of this journey, we can reflect on what endures and what has changed across these 1,000 years. What endures is consciousness, curiosity, and the drive to explore that has defined humanity since our ancestors first walked out of Africa. And these qualities persist regardless of physical form, whether we swim in alien oceans or exist as patterns of information in quantum computers. Language has diversified into hundreds of dialects and new tongues entirely. But communication continues, stories are told, and cultures evolve while maintaining threads connecting back to Earth. Art and music flourish on every world, each colony developing unique expressions shaped by local conditions. And the human need to create beauty remains constant, even as the forms it takes become wonderfully strange. Love and family persist. Communities form and support each other, and the social bonds that held us together on Earth still function across the light years, adapted but unbroken. What has changed is almost everything physical because the human body has proven remarkably plastic, adapting to low gravity, high gravity, red dwarf light, aquatic environments, and the digital realm through both natural selection and deliberate engineering. By 3125, there is no single human form anymore, but rather a family of related populations, some tall and willowy, others short and dense, some aquatic, some digital, all carrying forward the legacy of our species. Genetic diversity has exploded, and the gene pools of distant colonies have diverged to the point where interbreeding between some populations would be difficult or impossible. Yet we still consider ourselves one human family, united by culture and history, if not by biology. The definition of human has expanded to embrace this diversity, and most accept that consciousness and choice, not DNA, determine who belongs to our species. Picture one last scene from this future, a gathering in virtual space across the quantum network in the year 3125, where representatives from 70 star systems meet to celebrate the millennium of human spaceflight. They appear in forms both familiar and strange, baseline humans from Earth and Mars, aquatic humans from ocean worlds, space-adapted humans from orbital habitats, digital consciousnesses rendered in avatar form, and all speak through translation systems that bridge not just language, but conceptual frameworks. Together, they watch a presentation compiled from archives, showing the first lunar landing, the first Mars settlement, the launch of the first-generation ship, the arrival at Proxima Centauri, and many weep at seeing how far we have come, how much we have achieved through patience and collective effort. A child born on a world orbiting a red dwarf 30 light-years from Earth asks a simple question: what comes next? Where do we go from here? And the answer is both simple and infinite. We go onward, always onward, because that is what humans do. And the galaxy stretches before us with 400 billion stars, most hosting planets, many potentially habitable. Our current expansion has touched only the tiniest fraction of local space, a bubble 70 light-years across in a galaxy 100,000 light-years wide. And centuries of exploration still await us, worlds beyond counting. Some colonies will push toward the galactic core, others toward the rim, and, given enough time, humanity might eventually spread throughout the entire Milky Way, a process requiring hundreds of thousands of years, but entirely possible. We might encounter other intelligences, other civilizations also spreading through the stars. And that meeting will test everything we have learned about diversity, communication, and coexistence. But these grand futures remain distant possibilities, and tonight we rest with the achievement of the first millennium, the transformation from a species bound to one world to a civilization spanning the stars. Every person who lives on a distant world, every child born under an alien sun, carries forward the dreams of those who first looked up and wondered what lay beyond. The journey has been long, often difficult, sometimes marked by failure and loss, but also filled with wonder, discovery, and the profound satisfaction of achieving what once seemed impossible. We stand now as a mature spacefaring civilization, no longer taking tentative steps but striding confidently into the cosmic future. And the story continues, written by generations, yet unborn on worlds, yet undiscovered. Remember that this future is not predetermined, it is one possibility among many. And the choices we make today and tomorrow shape whether humanity reaches for the stars or remains earthbound. The technology exists or is within reach. Fusion power and generation ships are not fantasy, but engineering challenges. And the will to attempt the journey depends on whether we value long-term thinking and collective effort over short-term gains. This story of the next 1,000 years is an invitation, a vision of what we might become if we choose patience, cooperation, and the courage to venture into the unknown. And it begins not in the distant future, but in the decisions we make now. So, as this journey ends and you prepare to rest, carry with you the knowledge that the stars are not impossibly distant, that human footsteps might one day echo across worlds we can see tonight in the sky. The drowsy astronaut thanks you for joining this long voyage through time and space, and I hope it has given you not just facts and projections, but a sense of wonder about what humanity might achieve. Sleep well, dream of alien worlds and distant futures, and know that somewhere in the centuries ahead, someone might look back at this moment and marvel at how it all began. The journey continues, always continues, across the infinite frontier, and the stars await, patient and eternal, for the day we reach them.